Section 4.5 Optimization Problems. Optimization is a process of determining the best solution to a problem. Mostly, we're going to maximize or minimize some quantity. The optimization problems in general would be something like what is the maximum or the minimum value of an objective function subject to the given constraint. The quantity that we wish to maximize or minimize is called the objective function, and the condition is called a constraint. Guidelines for optimization problems. First, read the problem carefully, identify the variables, and organize the given information with a picture. If the picture is not provided, just draw one based on information in the problem. Number two, identify the objective function, which is the function to be optimized, looking for the key terms such as the minimum value of the quantity, the least, or the smallest. Write it in terms of the variables that you identify in step 1. Step 3, identify the constraint. The constraint is the condition that show you the relationship of the variables. So write them in terms of the variables that you identify in step 1. Step 4, use the constraint to eliminate all but one independent variable of the objective. So then the objective function will be just the function of one variable or the function of a single variable. Then find the interval of interest for that variable. Number 6, use the method of calculus to find the absolute maximum minimum value of the objective function on the interval of interest. If necessary, check the endpoints. The first example, we are going to maximize the area of the rectangle. Of all rectangle with a parameter of 10 meters, which one has the maximum area? Another way, we are looking for the dimensions of the rectangle that give the maximum area with the condition that the parameter of 10 meters. First, draw the diagram or draw the picture of the rectangle. Identify the variables. Since we are looking at the dimensions and in general for the area, we use A as the area and the area is from the length times the width. So we're gonna use the x as the length and the y as the width, and the area is x times y or the length times width. Of all rectangles with a parameter of 10 meters, that is the constraint of this problem. The constraint, the parameter, which is the sum of all measurements or the measurements surrounding the figure. Then the constraint, which is the parameter or the x plus y equals 10. We can write as 2x plus 2y equals 10. The constraint function shows the relationship of the two variables, which are x and y. Simplify by dividing all terms with the number 2. We get x plus y equals 5. We can rewrite y in terms of x or x in terms of y. Let's write y in terms of x, or y equals 5 minus x, and set it aside. So this equation is obtained from the constraint. So the goal is to find dimensions that the rectangle has the maximum area. The key term in this problem is maximum of the area. The maximum is the optimal term. So the goal is to optimize the area. The objective is to maximize the area. Then the area is the function for the objective. As area A equals length times width or x times y, so we rewrite y in terms of x, then the area becomes x times 5 minus x. And this is the equation that we are going to find or to look for the dimensions that give the maximum area. Next, we're gonna find the interval of interest from the equation from the function a equals x times 5 minus x. For the problem involving the dimension has to be greater than or equal to 0, including 0. Then, since the length times the width give the area, so the length, which is the x, has to be greater than or equal to 0. Also, the width, which is 5 minus x, has to be greater than or equal to 0 as well. Therefore, with these two conditions, we get x will be between 0 and 5. So x between 0 and 5 is the interval of interest. The next step, we're gonna find or locate the absolute max, absolute min, and use the process that we're gonna first find the critical number from the objective function a as a function of the x equals x multiplied by 5 minus x. Find the critical number by using the first derivative of the a, or a prime of x equals. Before we get the a prime, let's expand the a of x as a polynomial. So x times 5 is 5x, x times x is x squared with a negative sign. So the a prime is easier or less complicated to find the a prime. Or the other way we say without using the product rule to find the derivative. So the a prime is 5 minus 2x. This is a polynomial function. The critical value can be found from the case that a prime equals 0. Then solve for x equals 5 over 2 or 2.5. And the number x equals 2.5 is on the interval 0, 5, which is the open interval of the interval of interest. Next, we're gonna find the absolute max, absolute min, or look for the x that give the maximum area. It's gonna compute a at x equals 2.5, which is the critical number, and also at two ends, which is x equals 0 and x equals 5. At x equals 2.5, the a at 2.5 equals 2.5 times 5 minus 2.5, which is 6.25. The unit is the meter squared. And then for the area at 0 or at the one of the endpoints going to be 0, the area at the other end also 0. Therefore, we get the absolute maximum. This case is absolute maximum area occurs at x equals 2.5. The problem asks for the dimensions. Then the dimension of the rectangle that satisfy the perimeter of 10 meters and give the maximum area would be the dimension like x equals 2.5 meter and y equals 2.5 meters. From the relationship that y equals 5 minus x.